Okay, so let me introduce Rui Fernandes. He is from University of Illinois at Urbana, and he's going to talk about global solutions to Cartan's realization problem.
Okay, thank you very much. Before we get to this, getting to the end of a nice week, very nice week. It's amazing that so many of you are still here after last night. I'll try not to speak too loud so some can take a... Anyway, I think I want to thank the organizers, and I want to thank in particular Henrique Bursztyn for organizing the conference. He's the main organizer. The poster session is already over, but I have here a poster for him. So can you come down and open your poster? It's a poster. And I want to give this to him in name of all the participants. Thank you very much. But you have to open it. Now. It's tough to open it. So this talk today is it's really a double talk by myself and Ivan Strukiner. I was planning to, you can make noise, Henrique, no worries. I was planning to talk about something else, but I visited Ivan a few weeks ago, and turn it upside down. Henrique is a big baseball fan, so. Okay, so the thing is, every time either me or Ivan try to talk about this subject, we always feel it's like too short a time, because there is quite a bit of build-up, and then we always feel a bit frustrated that we get to the end and we don't have the message. So this time we are trying to see if 2 times 15 minutes is enough to give you the message. So the way this is going to go, I'm going to start with some very elementary things about G structures, because we need G structures over orbifolds, but it's going to be very fast. Then I'm going to give you an example of the type of problems that we can handle using these methods. And then I'm going to abstract from that example the general type of problem. And for starting from that, we are going to start seeing what is the kind of structure underlying those problems. And that's really the new thing. These kind of problems have been around for a long time. And we are going to explore the structure underlying the problem to solve the problem. And one of the main features of the theory is that it can handle global solutions. So in the Riemannian case, it's good, for example, to detect complete solutions, which in general is a very hard problem. Okay, so as I said, the aim is to find solutions to this Cartan realization problem. And the way we are going to do this is through some build-up, is really a theory of groupoids and algebroids with some extra structure, which we call G-structure groupoids and G-structure algebroids. So that's the plan, but let's ignore that. In principle, I should do the green part and Ivan the red part. Let's see if that goes. So let's start then with something very standard. So if you have usually a principal action is defined as a proper free action of a group on a manifold. But because we're going to relax this a little bit, and we're going to allow proper effective actions. So the effect of that, and locally free. So it's not globally free, but it's locally free, proper, and effective. So the effect of that is that the quotient is not a manifold, but it's an orbifold. It's an effective orbifold. So what you should think of P is of P as a principal G bundle over M, over an effective orbifold. Okay? So if you want, that's the definition of a principal G bundle over effective orbifold. All orbifolds will be effective. So you basically can do with the principal bundles over orbifolds everything you can do with principal bundles over manifolds. So you can talk, for example, about connection, either by giving an horizontal distribution, which is G invariant, or by giving a connection one form. Now, one thing is, for the theory, we really don't need G to be compact or connected, but for the purpose of these talks, you can assume that G is compact and connected. All right, so our main objects will be G structures. So if I have, for an effective orbifold, just like for an ordinary manifold, we can talk about a frame bundle. And it turns out that the frame bundle is actually a smooth manifold, the frame bundle of an effective orbifold. And in fact, it is a principal G bundle, well, with its structure group, the general linear group, in the sense of the previous slide. So that's the frame bundle, and whenever we have a closed subgroup of the general linear group, we can look at reductions of the frame bundle, and that's what a G structure is, a G structure over an orbifold. And as in the smooth case, this G structure comes with a canonical one form with values in Rn, n is the dimension of the base, which is very tautological. So the definition is there, so you pick a tangent vector, you project by the projection, and then you use the fact that the points of your manifold are frames to identify that tangent vector with a vector in Rn. So this satisfies two important properties. One, it is horizontal, so it vanishes if and only if the vector is the infinitesimal generator of some element in the Lie algebra, and it's G equivariant. So if you pull back the form by the action of an element in the group, you get the same things acting by that element via the canonical representation of, because G is a subgroup of GLN, so acting on Rn. And the -1 there is because our actions are always right actions. Now, the tautological form is very important because it's what allows you to characterize which principal bundles are G structures. So if you have a principal G bundle where G is a closed subgroup of GLN, it will be a G structure if and only if it carries a form which has exactly these two properties, that it's strong horizontal and which is G equivariant. Okay? So this is a very well-known fact about G structures, but I thought I should start by recalling that. Another very basic thing is whenever you have a diffeomorphism on the base, this induces a diffeomorphism between frames, and so you can lift it. And given two G structures, we say that they are equivalent if there is some diffeomorphism whose lift maps one G structure to another G structure. And so the basic problem is to understand when are two G structures equivalent or maybe locally equivalent. So this kind of problem is, why is this interesting? Well, because this really allows you to treat many different types of geometric problems, geometric equivalence problems, under the same language. So if you wanted to deal with equivalence of Riemannian structures, these are ON structures. If you want to deal with equivalence of almost complex structures, these are GLNC structures, and so on. Of course, if you want to remove the almost from there, you have to add some integrability conditions. but let's not care about that now. Okay, I think that's the end of my summary about G structures over orbifolds. It was just a small, quick reminder. So, oh, one more thing, yeah. So if on a G structure I put a connection, these satisfy structure equations. So the differential of the tautological form and the differential of the connection one form can be expressed in terms of theta and omega, because these together, they form a coframe for the manifold. So since they form a coframe, any form can be expressed in terms of these bases of this coframe. And so the structure equation is really just expressing the differential of these two forms in terms of that basis. And so here it appears two things. One is the torsion, and the other thing is the curvature, which we are viewing in this way as homomorphism from wedge 2 of Rn into Rn, or homomorphisms of wedge 2 of Rn into G. So here, for example, theta takes values in Rn, so this theta wedge theta, you should think of it as taking values in wedge 2 of Rn, and then you apply C, and you get something with values in Rn, and so that matches the d theta there. Okay. Oh, that's just a mistake. It should be omega. So there are papers where we used theta for the connection. That's annulled, sorry. Yeah. So there should be omega. Thanks. Okay, so let's get back to let's get now to really start things. Let's look at an example of the type of problems that we like to deal with. So in this example, first, just a general definition. If I have a Kähler manifold, so I have a Riemannian structure G, symplectic form omega, and complex structure J, and I denote the scalar curvature of the metric by R, this Kähler manifold is called extremal, or the metric is called extremal, if the Hamiltonian vector field of the scalar curvature is an infinitesimal isometry. So the reason for this name comes from the fact that these are critical points of a certain functional on the matrix, where the metrics are constrained to be on a certain Kähler class. So problem, classify extremal metrics on a manifold. Now, that's actually too hard, but let's do this on a two-dimensional manifold, on two-dimensional real manifold, real two-dimensional manifold. So what are the extremal Kähler metrics on a two-dimensional surface? That's the kind of equivalence problem we like to solve. Okay? And in fact, we like to find all two-dimensional manifolds with an extremal Kähler metric. Maybe a complete extremal Kähler metric. What are those? How do you find those? Okay, so the first part of the problem is to do what's called the differential analysis. And this differential analysis, that's where you go up to the G structure. So because I'm in the Kähler case, the G structure is going to be a UN G structure. So the group G is going to be UN. So we're going to use the unitary frame bundle. So here, P denotes the unitary frame bundle, and I have my connection one form that comes from the fact that I have my metric, and I have the tautological one form because this is a G structure. So the first two equations is the equations that I always have because I have a connection and the tautological one form. So those are forced there. But now, in the situation that we have here, there is this K over 2, and K here is just the Gauss curvature, which is the scalar curvature divided by 2. Okay. But so these equations are forced by us because we always have these equations. But now the point is that we have this extra function there, K, so let's differentiate this function. And I'm going to differentiate this function, and I have to express it in terms of my theta and omega. Now here, there is one thing that maybe I should have already said, which is the base is two-dimensional, so I should have here R2, but because we are in this complex situation, we can actually put there C, right? And IR is just the Lie algebra of U1. Okay? So let's see. Maybe now I want to use the board. So I want to explain that if I take the differential of k, sorry, I'm going one step too hard, it appears an expression like the one it's up there. So why is that? Well, if you take the pullback of the symplectic form up to the total space of the unitary frame bundle, then this is given by I over 2 theta wedge theta bar. Now, there exists also a lift, a unique lift of the Hamiltonian vector field of the Gaussian curvature K, so such that, so when you project this, you get xk. And the Lie derivative of theta along this lift is 0. That's what characterizes the lift. Okay? So, well, just using so in particular, so if I take the contraction of pi star omega, this is going to be the differential of k. And so k here, I'm viewing k as a function on the, and pull back k, which a priori is on M, to a function on the total space of the unitary frame bundle. All right, so using these two equations, what do we get? Or actually, this, right? Well, if I contract this with xk, I will get that the differential of k is contraction with theta times theta bar with a minus I over 2 here, plus I over 2 e contraction with theta times theta. So if I define my t to be I over 2 theta of xk, I get the equation I wrote upstairs. And what is t? Well, t here is a function defined on the total space of the unitary frame bundle with values in C. Okay? Now, we got a new function t here. So you may want to know, what is the differential of t? Well, the differential of t can be certainly expressed in terms of theta and omega, or theta, theta bar, and omega, right? The two components of theta. So we go on. So this was t. So let's see, differential of t, I over 2, differential of this contraction, Cartan magic formula, using the fact that this is 0, minus I over 2, d theta. But now d theta is given by the first equation upstairs. So this gives me minus I over 2, contraction of omega, minus I over 2, contraction of theta with omega. I think there's a plus here. And so if I call this u, I get the equation upstairs because this was t. Okay? So what is u? Well, u is a new function on P with values in R. Well, I got one extra function, so I have to differentiate u again. So this doesn't look like it ends, except that I have a bracket there that finishes in the next one, so it actually ends. So you differentiate u, and maybe I will skip this. I will leave that as an exercise. Figure out that the differential of u is given by that. So that's it. I haven't used yet the characterizing property of extremal Kähler metric, which is that the Hamiltonian vector field of the curvature is an infinitesimal isometry. So that is going to give us an equation that says that the Lie derivative of xk along theta is 0. Omega, sorry, not theta, the connection one form.
So the equations suggest that whatever u and k square, right, they are proportional?
Yeah. So you already see that there is some relation between u and k. Yes. Correct. So that's the equations you get when you move upstairs, right? So the classification problem is equivalent to the following problem. We have to find U1 structures with a connection. It will have a tautological form because it's a U1 structure, and some functions, KTU, so I didn't, which goes from P to the direct sum of R with C and R, such that those equations hold. So it looks much more complicated than the original problem. The original problem was so cute. That thing looks much more complicated. But that's actually what we want to solve. And that's actually what we can solve. So that's the typical thing. And so we want to find all solutions of that problem. All manifolds. The manifold is also part of the problem. I'm not giving you the manifold. Okay? Now, that's a bit weird because you look at that. Yeah.
Is it obvious that the problems are equivalent?
Yeah, if you solve that, you found the unitary frame bundle of your solution. The base is going to be a Kähler manifold with an extremal metric. So it's really equivalent. Okay? Okay, but so as I said, the P is also part of the unknown. We don't know what P is. But now this becomes weird. If I don't know what P is, how can I even write those equations? So our formalism will provide a way of having those equations making sense even without knowing P a priori. Okay? So let me write in the blackboard the general problem that you may now compare with those equations and see that it makes at least some sense. It's not completely rubbish. So this is the general. So this is the realization problem of the title of the talk. So we are given some data. What is the data? So we call that Cartan data. And the Cartan data consists of the following. Well, a closed subgroup of GLN, which is really connected with the type of problem we are looking at. Are we looking for metrics? Are we looking for Kähler metrics? Are we looking for symplectic forms? Are we looking for contact structures? Whatever. That's going to determine the type of G structure, and so the G that we are working with. We're going to have an X. That's a manifold. It's actually a G manifold. So there will be and this is just for future notation, every time you see a psi, that means the infinitesimal action associated with this G action. Okay, so let me write this as, as a morphism like this. And the remaining piece of data is G equivariant maps. Called C. R. And F. Well, this is the torsion. This is like the curvature. And this map F is something else, as you'll see. So that's our data. And we'd like to have solutions. So what are the solutions? Solutions is an orbifold, a G structure over this orbifold, and so let's denote a G structure with connection. So you have the corresponding tautological form and the corresponding connection form. And the G equivariant map such that the following equations are satisfied. Well, surprise, surprise. Yeah? I'm sorry? Oh. Thanks. So such that the following equations are satisfied. Well, we saw these equations before. So that's just the structure equations that always have to hold. And finally, the H so this was the infinitesimal action. This was this F extra comes in. So the H in this problem consists of this map from P to R plus C plus IR. So in the problem over there, X is R plus C plus IR. Okay? So that's the abstract realization problem. That's the problem you want to solve. So this is just what I wrote in the blackboard. And so this is the kind of things that we like to know. We like to characterize all solutions of this problem up to equivalence. We like to determine the group of symmetries or the Lie algebra symmetries of solutions. Well, better, we like to find the moduli space of solutions. Okay? And we like to know if complete solutions exist. In the metric case, complete should be like Riemannian complete solutions. X in the example is, I'm going to write it down, but it's R plus C plus IR. That's X. Okay? So it's anything but obvious when you started with your problem. But it's the space where these functions that appear there takes values, the K, T, and U. Okay? So that comes from the differential analysis of the problem, figure out what x is. All right, so that's the aims. Okay, so here's the first remark, is that associated to such a problem, you can find an algebroid. So this remark is really due to Bryant in an appendix on a paper where he does classification of what's called Bochner-Kähler metrics. At the end of the paper is a very long paper, has 90 pages or something. And at the very end of the paper, he has an appendix where he talks about this realization problem and where he writes this algebroid. So maybe I'll copy the algebroid to the blackboard. So it gives you a little bit of time to see. So I start with my Cartan data, and associated with my Cartan data, I have an algebroid, which maybe looks a little bit weird a priori, but I'll try to illuminate this a little bit. So as a vector bundle is really a trivial vector bundle with fiber Rn and G. It's a vector bundle over X. And what did I write first? The anchor. So we have this anchor map from A to Tx, and the anchor map is really made of the map F and the infinitesimal action. And it's really just there for you. So if I have a pair U alpha, or X U alpha, then I'm taking F of U at X, really F of XU plus psi of X alpha. That's a tension factor. Okay? And then there is a bracket. And the bracket, we start by defining the bracket first on constant sections. So if I have a pair U alpha and V beta, there is a first component of the bracket which takes advantage of the fact that we are working with a subgroup of GLN. So if I have the Lie algebra, it's a subalgebra of GLN, so I can act on vectors in Rn. So this is the formula for the bracket. Sorry, this is, what am I writing? Alpha v minus beta u minus c u v. So that's where the torsion appears. And here I use also the bracket in the Lie algebra, and I subtract the curvature. Okay. So this defines the bracket on constant sections, but then I can define this on any sections because I already have an anchor map by imposing Leibniz. Now, actually, I'm cheating a little bit because there is no reason why this bracket satisfies Jacobi. So in fact, it may fail if you are just given arbitrary data, as I did there. Okay, so if you start with this Cartan data, you define this vector bundle with this bracket and this anchor. In general, it will not satisfy Jacobi identity. Now, why on hell does one define things that way? Now, remember, you can define an algebroid. Instead of giving the anchor and the bracket, you can give the differential, right? The differential on forms. So that doesn't depend on the Jacobi. If I have something it's like an algebra but doesn't find Jacobi, I look at it, it still has a differential. It just doesn't square to 0, but it has a differential. So what is the differential associated with that data? Well, it's the following. So it's going to be a differential operator of degree 1. And if I apply to the projection of A in Rn, that's really like a bunch of one forms, and one forms. If I apply the differential, that's what I get. Okay? And if I apply to the projection of A in G, so that's against a bunch of one forms, the differential is given by this. And if I apply to any function, the differential is going to be given by this. Well, this is only on one forms and functions, but this is a basis of one forms. These two projections give you a basis of one forms. So I can extend this to any A form by imposing Leibniz. Okay? So I'm claiming that if you start with this data, it's just the same thing as starting with this data. And this is exactly the equations we want to be satisfied. Okay? So this is not some magic thing. This is really trying to make sense of this when we don't have our total space of the G structure. What we are left with is with this data. Okay? And this makes sense once we have our Cartan data. All right, now there is this issue that Jacobi may fail, so this differential may not square to 0. So the first theorem, well, before that, so this is in the example that I started, that's the algebroid. So X is R times C times R with coordinates KTU. A is just a trivial bundle with fiber C plus IR, so it's a rank 3 vector bundle. The bracket on constant sections is given by this nice formula, and this is the anchor. Okay. All right. So, as I said, the Jacobi may fail, but here's the result. If I start with Cartan data, and if I know that for any point x in X, I can find a solution that takes that value, then this thing actually will satisfy the Jacobi identity. The differential will actually square to 0. Okay? Now, that's actually very simple to see why. Because, so that's the next remark. What happens if I have a solution? Well, if I have a solution, I have this map from this manifold to this manifold, but I also have these two things. So out of this solution, I can construct a map from the tangent to Fg using theta and omega to my A, which was x times Rn plus G. And this will be a map, a bundle map covering H. So a solution gives me such a map. And the fact that I've defined the algebroid in that way, with the differential giving that formula, will tell us that this map actually pulls back the differential of A to the Durand differential, if this is a solution. Let's call this. How do we call this, Eva? Huh? Var phi. Okay. So if this thing exists for every point, it will imply that dA squares to 0. It's also teaching you something. It's teaching you that solutions are really algebroid maps from here to there. So to find the solutions, you have to find those algebroid maps. Okay? So, what have we done? Well, what we have done is that from Cartan data admitting solutions, we have construct an algebroid A. Now, the point is that this algebroid has more structure than just an ordinary algebroid. So this algebroid comes with several things. So we already actually saw it before. You see, the algebroid had these projections, this theta A and this omega A. These are really like analogous to tautological one form and connection one form, right? The other thing that the algebroid has is that we started with G, a subgroup of GLN, and GLN acts on Rn by the defining representation, and G acts on G on the Lie algebra by the adjoint action. So this algebroid actually also comes with an action of G. So at this point, we only suspect that there is something going on with this algebroid. There is some structure that it's related with this group, the presence of this group and the presence of these two forms. So what I want to explain now is this correspondence. Well, I already saw that out of these, we can get an algebroid. But I'm saying that I get some kind of G-structure algebroid with connection. What is that? So that's what I want to explain next. Okay? So now I'm going to go away from this problem, and I'm going to build a theory of G-structured groupoids with connection and G-structured algebroids with connection. Now, the way you should think about this theory is as follows. What we are looking at when we are looking for solutions of these is we are looking for principal bundles. So it's really like thinking you are looking at families of principal bundles. So the way we're going to set this up is I'm going to think about my groupoids as giving me families of principal bundles. These families is going to be the source fibers of the groupoid. And you say, why do you care about families that are source fibers of groupoids? Well, because we have an infinitesimal description of these families, which is this algebroid. So if I want to have an infinitesimal description, I cannot start with an arbitrary family of principal bundles. I have to have something. So the something is the fact that behind this family, there is a groupoid. And the family is the source fibers of the groupoid. Okay? So that's what you should keep in mind. And then there is coming more, but probably that will be with Ivan. So here's a definition. A G-principal groupoid. So it's a groupoid with a principal action along the fibers. A principal actually in the sense that I started in the first slide. Okay? And this action is compatible with the groupoid multiplication in a funny way. So if I act G on this composition of arrows, it only acts on the first arrow. Remember, I want the action to be along the source fibers. And so that kind of forces that. Well, anyway, so that's the definition of a G-principal groupoid. And the morphism of G-principal groupoids is the obvious thing. It's a morphism between groupoids that preserves, between G-principal groupoids that is G-equivariant. Now, this is not the most efficient way when we want to go infinitesimally, but so there is an equivalent way of defining G-principal groupoids, which is as follows. So I think now I can remove this. So the first thing is that out of these actions on the total space of the groupoid, we can build an action on X, on the base of the groupoid. So we have this groupoid, and I'm going to define a G action on X by saying that G acts, so these are right actions always. G acts on X by G acting on the identity at X. Now this will not be an identity, so I take the target of this. And so out of my action on the total space, I get an action on G. Okay? And let's see. What do I want to say here? Right. So I also get what we call an action morphism. So this is a groupoid morphism. So now I have an action on X. I can form this action groupoid. And I claim that there is an obvious groupoid morphism from the action groupoid to gamma. And this will take Gx to the identity times G. And this action satisfies three things. So it's a groupoid morphism. It's effective. So that means that the kernel of alpha. So I call this iota, actually. So the kernel of iota is different from the x times, if you want, x times e. And 3, it's local injective. So I'll let you figure out what local injective means. I mean, it means it's injective, but only when these things are small, right? Now, when I have this action morphism, I also get a new action of G on gamma. Now, the original action satisfies that property, so it's clearly not an action by automorphism of the groupoid. But now I can build an action by automorphism of the groupoid by using this action morphism. Sorry. So let's see. Yeah. And so this is an action by groupoid automorphism. Okay. Anyway, the important thing is out of that, I got this G action on X and this action morphism. And now, if I have this, I can reconstruct the action of G on X. So it is equivalent to give a G principal groupoid and to give such a data, a G action on X and an action morphism, okay? Which satisfies these properties. So that's the next thing. And so this is this correspondence between principal groupoid actions and groupoid morphisms, which are local injective and effective. And again, I stress, the way you should think of this is that what we are doing is we are parameterizing via the source map a family of G principal bundles. Okay? All right. Now, with these, we can play the game because we really just have a family. So now we can look at families of all objects that we have for principal bundles. So I can look at connections. So if you want to, we can define by a connection via connection one form. So what is a connection one form on a G principal groupoid? Well, it will be a one form with values in the Lie algebra, but it's a right invariant one form. So right invariant one forms only apply to vectors tangent to the source fibers. Okay? So this is really a source foliated one form with values in G. And it should satisfy the usual properties of a connection. So it's vertical, so if I apply to the infinitesimal generator of the action, it returns to me the element defining the infinitesimal generator, and it should be G equivariant. And so if I have a G principal groupoid with connection, what I have is really a family of G principal bundles with connection. That's it. Okay? Now, I don't want just ordinary principal bundles. I want families of G structures. So how can I get families of G structures? Well, remember, a G structure is really just a principal bundle with a tautological one form. So we abstract the properties of a tautological one form to a G principal groupoid. So if I have a subgroup of GLN, a closed subgroup of GLN, a G structured groupoid, which is going to be a G principal groupoid, together with a one form, which is going to be right invariant, so it's only along the source fibers, takes values in Rn, and it satisfies the properties that I need to be a tautological form. So horizontal and G equivariant. And so again, this is just really a family of G structures. Okay? And now you can check that this, of course, satisfies some familiar equations. So if I start with a G structure groupoid with connection, the tautological form and the connection one form satisfy these structural equations where appears something that should be called the torsion and the curvature. Okay. Now, all the definitions that I've made are made in a way that you can infinitesimally or infinitesimalize them, right? You can go to the algebroid level. So what is a G-principal algebroid? Well, I take this approach of G-principal groupoids via action morphisms, so I just take the infinitesimal version. So it will be an algebroid with the G-action by automorphism and an injective morphism satisfying what? So if I have a G-action on an algebroid by automorphisms, this defines for me a map which I'm calling there phi hat from the Lie algebra to the derivations of the algebroid, the infinitesimal version of the action. Okay. And so what I'm requiring is I have a G action on A by algebroids automorphisms, and this G action comes in a way that all these derivations are inner derivations given by these algebroid morphisms. And that's the infinitesimal version of the object we had before. And then you have the notion of a morphism of G-principal algebroids. Should be something that intertwines these action morphisms and intertwines the G actions. And also you have the notion of connection one form at this infinitesimal level. Remember the connection one forms, they were right invariant one forms. So they are completely actually determined by something at the algebroid level, by an A connection. So a connection one form is going to be just an A form on the algebroid with values in G. It should be vertical, which now is what? Well, we can use this action morphism, and vertical just means that if I apply my connection to elements of A coming from here, I recover the alpha. It's like the infinitesimal generator. And it should be G equivariant, as before. If I pull back the form via the action of G, it should give me back at inverse. Well, now you can almost guess what would be the G-structure algebroid. Right? So what should be a G-structure algebroid? It should be a G-principal algebroid with a tautological one form, with the infinitesimal version of a tautological one form. So that's what it is. So a G-structure algebroid is a G-principal algebroid. We keep with a fiber-wise surjective A form with values in Rn. It should be horizontal. So the tautological form vanishes if and only if this thing is like an infinitesimal generator. It's given by this action morphism. And the G equivariance holds. And you have the infinitesimal version of the structure equations. Now using the algebroid differential. So if I start with the G-structure algebroid with connection, and with I have the tautological form and the connection one form, and I get the familiar equations for some appropriate definitions of the torsion and the curvature, which is given there. Okay? Now, as you can expect, there should be, well, before this, there is a differentiation process, which is not very surprising. So if I start with the G-principal groupoid, I can differentiate and get a G-principal algebroid. So I get this Lie functor. And this is the mother of the functors, but of course I can restrict this to G-principal algebroid. I can add a connection, and I will have a connection here. And I can, instead of taking principal, I can take structure groupoids, and I will get G-structure groupoids. G-structure algebroids, eventually with connection. So now you can ask about Lee's first theorem, Lee's second theorem, and Lee's third theorem. And basically, things go as almost expected. So the first thing is if I have a G-principal groupoid, you may think, yeah, there exists a unique source-simply connected G-principal groupoid. Well, not so fast. What it exists is a unique source-connected G-principal groupoid with the same algebroid, but now the condition of source fibers being simply connected is replaced by the conditions that this quotient is simply connected. Now, this quotient is not a manifold, it's an orbifold. But so simply connected means the orbifold fundamental group is trivial. But the result is still true. There is a unique maximal G integration. So this is called the canonical G integration, which is smaller than the usual integration. And the second Lie theorem is also true. Well, now you know what is the condition that you should require in the first groupoid. In the usual theorem, you will require this to be source simply connected. Now we need this to be these simply connected. These things have to be simply connected. But Lie 3 fails, as you would expect, but it fails even in a more fundamental way, which is you start with an algebroid, a G-principal algebroid, and the algebroid is integrable, but it may fail to be G-integrable. And so Ivan will explain that. The last thing is, why is this relevant for whatever I said at the beginning? Well, because of this canonical form for G-structured algebroids. So if I start with a G-structured algebroid with connection, I can use my connection one form and my tautological one form to get a canonical isomorphism, so no choices, with x times Rn plus G. Okay? And when I use this isomorphism, the G action on A becomes just the standard actions on Rn and on the Lie algebra. And this is the action on G that is given. The action morphism becomes just the inclusion of this thing in A. The tautological form becomes the projection that we saw played some role. The connection one form becomes the projection in G. And these equations are satisfied for some maps, G-equivariant maps. So G-structured algebroids with connection are exactly the objects that codify Cartan data. Okay? And that's why we care about them. Now, why do we care about the corresponding global versions is because of solutions. But that's going to come in the next talk. So let's stop there.